All right. So notice that we've been very, like, what's the word, cagey about like what happens at the endpoints. You guys are really good at radius of convergence. Let's return back to that conversation from Monday. Did we just talk about that? Yeah, right? No, I'm losing. But whenever we talk about radius of convergence, we talk about the ratio test. You have that worksheet. And actually, I'll just tell you right now, the homework tonight, I have a worksheet, and all the problems are identical. And the instructions are just a little different. It says find the interval of convergence, not the radius of convergence. You've already found the radius of convergence, but we'd like to know, like, can we write down an inequality? That is, the thing that stopped us from writing down that inequality is what happens at the place. I know what happens in between, a distance of r away in between, but what happens if we're exactly a distance of r away on either side of our center? Does it converge or not? And that's like so complicated, we have like 2 days devoted to talking about it, okay? So this is like the L equals 1 case in the ratio test, if you will. Like, what happens if we're at that place? So if possible, eventually we'd like to be able to, in the end, write down the interval of convergence. That is, it converges from -2 less than or equal to x is less than 5 or something like that. We're going to be able to write down. So here's the first one we'll do, and we'll go through all the work. Find the interval of convergence for this series. I'm just going to tell you right now that if you do the ratio test, just to quicken the work here, that you will find that r equals, the radius of convergence is 4 for this, okay? So you can do the work and we'll you know, I assume that you're like getting decent at that, I don't know. Do the ratio test. It's not trivial to do the ratio test. It takes a little work to write that all out. But I'd like to make sure you know how to write that out formally. So remember what that says if we said the radius of convergence is 4. The center is 0. So I'd love to be able to say that, like, oh, well then this converges from -4 to 4. And the big question here again is, what about at -4 and at 4? That's the big question. Hopefully you're clear on like the question we're about to answer.
The radius of convergence is what we did earlier.
Radius convergence / ratio test is what we discussed earlier, yeah. So that's why I said I just skipped all the details. I just assumed that you know how to figure out from this that the radius convergence is 4. The center is 0, and the radius convergence is 4. That means that like this definitely converges if x is like 3.5, definitely converges. If x is 2, definitely converges. If x is -3.9, definitely converges.
Oh, okay.
Right? Any distance up to 4 away from 0, based on our previous discussions, we showed that this converges for any value up to, but not including 4 away from the center. Andy? No. Okay. So I have like a really novel idea. I have this idea where we like plug in -4 and 4 and just like see what we see, right? That's my big novel idea. Like let x be those things. Oh, where are my animations? Okay. Just pretend this reveals in a really climactic way, okay? So if we plug in -4 and 4, then we have the following 2 series that in fact don't have an x in anymore in them, right? So this is like now return to pre-calculus knowledge, really, right? Along with maybe some other, try and bring this back. The big question is, does this converge? Let's just say it right out, this first series, and then also we want to return to this series and ask, do these converge? Notice we can simplify those nicely. The questions we can rephrase in these ways. Does this converge? Does this converge? You see how I simplified those? You got a 4 to the end, a 4 to the end, cancels out, etc. But I think we can all pretty clearly say that they diverge, don't they? Think about, remember, just like think about what these mean. And if you're losing at any point during tuition, forget the sigma notation and start writing down. What is this? This series is -1 plus 2 minus 3, and like, I mean, I don't have to bring in a lot of heavy machinery here for us to be convinced that this definitely diverges. And this one, which is very simple, 1 plus 2 plus 3 plus 4, diverges also by the end term test, if you will. Again, I feel bad that my animation got broken or something. So that was supposed to be you coming up with that, but there it is. Okay. So the interval of convergence on this one, we can just hands down say it excludes -4 and 4, right? So now we can finally say it. Like we've been so, like I said, kind of cagey about it. We're like, well, the radius of convergence is 4. But now we can go all the way and be like, I can describe what this does for every real number x. If x is a number on this open interval, -4 to 4, converges, else diverges, right? Is that cool? If you give me a number, I now can tell you, no matter what number you give me, that this either converges or diverges. So we've kind of completed the story. Now, that was a good first example because it wasn't too bad. But sometimes the things we get, and this characterizes the process really well. Plug in the 2 endpoints and see what happens. That's the process. That isn't the entire process. But it just turns out that the thing we get is not always, like what it does is not always obvious. On that one, it wasn't too bad. How do we know when we have a series that just has like an n in it? How do we know whether it converges? Do you remember all these tests? They still come into play. Like the end term test is the one we just used. And I'll explain maybe a little bit more tomorrow why these all apply as well for series. I know that maybe you just remember that they do because it's a pre-calculus and you've heard some of these as well. But they work for all series as well. There's a helpful list of these along with a suggested order in which to apply them in your book. So I intentionally rendered that so small that you couldn't see it because I was like, I don't want you spending time copying that. You can like take a photo of your book if you like it, and just lists all these and reminds you what they are and kind of suggests an order to do it. I think the first one actually I can read it because I'm up close here. The first one is at the end term test. I think that's a great wise one. If it's obvious that the terms themselves diverge, have a limit, not 0, then they diverge. I think that's a great first line of defense that weeds out. So you can see why that might weeds out divergent series. So you can see why that might appear first on the flow chart, right? So it suggests not only what the tests are, but also suggests an order in which to apply them. It's not like, in fact, as you gain intuition on some of these problems, you might jump right in. If you know that it's got a series that's a form of the P series, you might jump right to there because you have some intuition. There's no please don't necessarily go through and apply each one. Okay, well next I apply this one, and if it doesn't work, then I apply this one. So you're gaining some intuition. So jump right to the one you know that works if you know one will work for you. All right, the next thing that we've talked about, and I think I'm trying to remember, well, I think we don't talk about this in pre-calculus, so this is worth mentioning. Okay, that's why I think I had it up here. The other ones I'm not putting back up here, like I assume you remember. What else did I put up there? Direct limit comparison test, all those kinds of the P series, comparing to harmonic series, all those kinds of things are things that you might remember. So, but this one I think is not one that we've ever talked about. So, so it's worth talking about. If we have an alternating series, it's called, and I think you can agree that this is an alternating series. And by alternating, I mean truly alternating. Can you imagine that no matter, imagine some expression for an here. That if you plug in certain n, comes out to be positive, and certain one comes out to be negative. Well, then maybe it's not alternating, right? Do you see why that could be? Maybe it's not strictly positive, then negative, then positive, then negative. So let's assume that each of these things is positive, so that, I don't know, one way or another, do you understand that they need to be truly plus, minus, okay? Because it could be possible that whatever dictates this an, could cancel out with one of those negatives and make 2 positive terms in a row. Well, then it's not really an alternating series, okay? So that's what this first bullet is requiring. It's kind of just guaranteeing. The first bullet is just guaranteeing that, yes, you really do have an alternating series. The next requirement is that each term be less than the previous term. Together, the first two you might say are decreasing in absolute value. You might say, or something like that. I don't know. And then we also require that the limit be 0. That's a natural thing to require because we already talked about the end of term test. And if all those things are true about your alternating series, that is to say, if it's truly alternating, if in absolute value it's decreasing, notice these are positive, so this makes sense based on the first requirement. And the limit is 0. You might ask, like, could those possibly not simultaneously ever be true? And the answer is like, yeah, but I can give you, I have an example written down in my notes that's like terrible that does that. So you actually do need all 3 requirements. Then the series will converge. Yeah.
For a to the n plus 1 is less than a to the n, does not mean that a to the n has to be between 0 and 1,
Mm.
or does this scenario going to be greater than 1?
I mean, the series could start with numbers like 7, and the next term could be like -5. In which case, is 7 is 5 less than, because we're talking about the terms themselves, an, are without the negatives, right? So the positive terms are 7 and then 5 and then etc. So is 5 less than 7? Yeah. So as long as that's true for not just those 2 terms, but every pair of terms is for each term it's less than, in absolute value, less than the previous term.
So a to the n plus something being multiplied by -1, it's just the whole term?
Yeah, I'm just saying, yeah, this is just like kind of a mathy way to write what I said earlier, and that is, please make sure it just alternates sign, right? And then if you take the absolute value of all those terms, which is another way of saying this here, are the terms in absolute value getting smaller, and is their limit 0? Then it's necessarily true that they will converge. Now, and I should actually say, before we go too long, that it would be good for me to write one of these down here. So for example, here's like the classic example, and it's usually like the go-to example too, I'll just say that right now. It'll come up lots and lots of times. This series, which is sometimes called, it looks a lot like the harmonic series, right? Like 1 over n. Except with the only difference being, which it just alternates sign. So we start with n equals 1. On this one, we better start with 1, right? But in general, no. Then it turns out this converges. Do you remember that this doesn't converge? I just want to make sure you have this in view here. So, and the reason this converges, and we didn't prove this result, maybe you could think about why this works. But this converges because of the alternating series test, and this is something I think that didn't really come up in your pre-calculus class at all. Are these terms, is the limit 0? If you put in really large numbers, you get things close to 0. So that last point is definitely check. Is it really an alternating series? Yeah, definitely. The terms are, if you want to write it, could you write it in that form? The answer is yeah. Yeah, you could definitely write it in that form. And what else needs to be true? Oh yeah, that in absolute value they get smaller. Yeah, because we have terms like 1/7 followed by a term like 1/8. So I think all things have been satisfied, and really, if you wanted to tell me that this converges, I need you to really say those 3 things, okay? If you're going to use this test, you need to tell me that the terms, you don't have to like justify it much more than that, you just be like, the terms decreasing absolute value, it is an alternating series, and the limit is 0, right? Therefore converges.
The second and third one, aren't they kind of given? Like, if one is true, the other is true?
Yeah, and I addressed that just with a little caveat a second ago. I said, the answer is no, actually, amazingly. I'll give you later, if I have time, I'll write, I concocted an example one year because someone asked for it, that has a limit of 0, but, or I forget, I had one of these that I made not true, and the other fails. So I'll show you that. Yeah, dude. It does. How did you know that? Because you're a math nerd. Okay. It converges to the natural log of 2, amazingly, is what this converges to. I think that, is it a natural log of 2 or natural log of 1/2? I don't know. Okay. Well, you should do a progressive approximations and tell me what that.
Natural log of 1/2 is just negative.
Yeah, that's what I'm wondering is which one. I might be off by negative. That's why I'm forgetting. So test it. Do you add up the first? Do you know how to do a sum on your calculator? Do like 1 to 100 and see if you get close to element 2. Well, you can't have n equals 0. So I don't know. Yeah. Play around with it. All right, this brings up another topic that I'd like to introduce these two words as well, that really we haven't really needed to talk about until right now. And this is called absolute versus conditional convergence. And again, the example I wrote over here on the board is the prime example of that. We would say that if you take the absolute value of this, then it doesn't converge, right? So we would say that this converges conditionally, but not absolutely. Okay. So I've said that here. If the absolute value of our series converges, then we say it converges absolutely. But if the series converges and yet the absolute value of the series doesn't converge, like the example I just did with the alternating harmonic series, then we say it converges conditionally. Yeah. Okay, that's only, I think it's maybe ln 1/2, yeah. Okay. But this is a piece of trivia. I don't know. I actually can't remember the proof. It's due to Euler, I think, but.
Like, what if it looks like everybody would look like x to the n over n? So you could kind of make all of them.
I think you could get it using some, maybe you could get it using the series for ln of like x plus 1 or something, and then plug in -1/2 or something. Play around with that. Yeah, I think that's maybe how you get it. I have to think about how that works. By the way, we should mention that actually, that little trick I just mentioned to Tyler. A lot of things like this sum, some of these sums that sound amazing to us. This one I think is due to Euler too. You've probably seen this before. Like the fact that we know that value that sum, a lot of those can come out to come from like series that you plug the appropriate number in and you get like the result. There's some really cool results that you can come out of. Now once we have an infinite series, like one thing we haven't done a lot recently is like take an infinite series and like actually plug something in, right? But when you do, you get some interesting infinite series results. Like you get infinite approximations for pi, stuff like that, right? So there's some cool results that can come out from some of these series if you choose, instead of have x's in them, just actually put a number in. You get like, whoa, this entire series like equals the square root of 2? What? I mean, it's also kind of revelatory, isn't it? Okay. So we should always back it away and like appreciate that. So let's make sure we do an example here. Okay. Do I have clicks on this? No, I don't. All right. So I have to go over on the board on this. I apologize. So do I give anything here? I do. Good. I give the rate to convergence. That's me being nice. But theoretically, I could just not tell you that, and it would be a really big problem, right? You'd have to do all the work to find the radius of convergence, and then you would find, then you would have to answer the question we're about to find. Okay. So what values are we wanting to? I mean, what are we doing? We're trying to find interval convergence. So what do we want to? The only question mark in our head is we know this converges absolutely on the interval for sure. What's the center? Is it obvious from the form? It should be obvious at 0, right? Because there's an x to the n. The rest is like our Cn, right? The rest is like our coefficient. You might want to hear this. This is like okay. So you're gonna like this. Okay. So I know that for sure it converges absolutely on -2 to 2. Why do I know that? If you did the work to find the radius of convergence, what did you do in the work you did? You did the ratio test, right? And when you did the ratio test, you stacked this term. You did n plus 1 all here. You replaced all the n's by n plus 1, and you put n in it as well. You stacked them. You took the limit of what? You took the limit of the absolute value of all of that. So what does that tell you when you're done? It tells you that if x happened to be a number like, I don't know, -1.3 or something, that it doesn't just conditionally converge, it definitely absolutely converges, because you did all the math there, assuming we're talking about the absolute value, right? Does that make sense? So we definitely know that it converges, whether you have an alternating series or not in between, or positive, negative, doesn't matter. No matter what, inside there, it converges. is you took the absolute value. I mean, it definitely converges for any value in there. Whether this was here or not is my point. Like if you did the ratio test, this piece right here, the -1 to the n+1, would just not matter. I know, my board is a mess. That's why I'm not. Use my finger. The -1 to the n+1, if you're doing the ratio test, can you feel, I mean, like I said, maybe we should have just done the ratio test. Kind of explaining it. If you're doing the ratio test, can you see how that would just immediately just not matter at all? Yeah. Yeah, the -1 to the n+1, if we could taking the absolute value right away when we do the ratio test, it just won't matter. So yeah, the point is this will like if you plug in a value like actually it's the positive values that it alternates. But the point is that even if it alternates, we're gonna take the absolute value and we show that it converges in a distance or two away maybe. So the only question left in our mind is what about if x equals -2 and at x equals 2. So here we go. We're going to think about the series in its form that it takes at those two values and investigate those individually. Yeah.
So for the ratio test, the column says absolute value of like x minus 2, like less than the radius and stuff like that. How would you do that?
So you get in the end of the ratio test, I mean when you do the ratio test and everything, at the end you'll get the absolute value of x is less than 2. So that tells us the rate of conversion is 2. And then any x value between -2 and 2 on the open interval, -2 to 2 converges.
If like, say that was an x minus 2, like within the like
Yeah.
absolute value.
Yep.
Of what we do.
That would be from on the open interval 0 to 4, right? Yeah. Would be just you move this interval somewhere else. But the rate of convergence is still 2. If 2 is what appeared on the right side of the inequality, then the rate of convergence is still 2. It's just with a different center, right? That's why radius is a good word for it. Okay, here, let's do this, and then I'll take your questions, because I want to make sure like we get really a good discussion about this one problem at least. Okay, so we got some work to do to like clean up this algebra here, but let's plug in -2. So we get -1 to the n+1 times -2 to the, I'm just going to blindly plug it in, and I'll think about what I wrote. -2 squared, 2 to the -2. All right, now I need to simplify that. So see if you can clean that up, if you will. You do the work for me, please. It'll be a little bit ahead of time. Here we're plugging in 2. N, excuse me. It's supposed to be an N. To the, no wait. Oh, yeah, that's n squared. And this is 2 to the n. I'm sorry. You're right. Only the x. Sorry. Good. So -2 and 2, that's the only part. We'll highlight it. This is the only part we changed. Yeah. Okay, good. So now we have to simplify those. Here we go. Don't rush it. Here we go. We get -1 to the n+1 times -1 to the n over n squared. We can do more there maybe. Here we get n equals 1 to infinity of, boom, just -1 to the n+1 over n squared. And actually maybe we like that. That's fine. What about this though? What can we do up there? That's going to be it's -1 to the, here you say 2n+1, which is -1 times -1 to the 2n. All right. Okay. So now I have some questions. Right? By the way, in fact, actually, we can do better than that. What's this? It's always 1, no matter what it is, right? It's always going to be positive. This is an even exponent. So I think we just have this series. Good. All right. This is making my life a little better now. That was a lot of thinking, but now I'm ready to like say something about these endpoints. Talk to me about this endpoint. converges, why? It's not alternating. But yeah, the P-series. This is, so this converges
Do you have to say why or do you have to say
because, no, you should say why. Yeah.
what
Because
is the P series? It's
1 over n squared
Oh. And then
converges. E equals 2, which is greater than 1. Okay. So, and you could say P-series test. Okay? Down here, this is the new piece, right? This, well, actually, we don't even need that here, do we? It is alternating, but do we even need, well, no, we'll still say, this converges, there are a couple ways you can say it, I guess, but we'll use the alternating series test here. So, here, we'll write it this way. Since, good practice here. Since this is an alternating series, yeah, the only thing is with the absolute value piece, you have to, the other thing I should have said is if a series converges absolutely, then it definitely, if a series let me make sure I say this right. If a series converges absolutely, then it definitely will converge conditionally. I don't think I had that result up there. With terms that decrease in absolute value to 0. You see the limit? I need them to be going towards 0. I need them to be decreasing in absolute value, and I need to be an alternating series. This converges. All right, so therefore, I can actually come out and say the interval convergence is the closed interval, -2 to 2. Is that okay?
So what is
So because we already, so in fact, it's actually, it converges, and it converges absolutely on those. It actually, we didn't know that originally, but actually we can update this. It converges absolutely on the entire thing, right? Because if you, outside of that, it diverges. Because if you take the absolute value of this, you get that, right? So like I said, I did the alternating series test here, but you don't have to for this one. Like you could just take the absolute value of this and see that it converges. Well, then this will definitely converge too. Yeah.
the whole point of the x equals x equals 2 is determined at the endpoint?
The whole process is only at the 2 endpoints. Like it's like a terrible amount of work to just establish the convergence at endpoints. Yeah, it's a pain. Yeah. Let's see if we can at least point you in the right direction on this one, Helen.
I was gonna ask if you could give an example of something that's conditionally converted.
Yeah, so I don't know that we'll get through this one, but this is an example of that it's conditionally convergent at one of the endpoints and not the other. And the only way I'd have to modify this problem is to make this like a -1 over n, and this to be a -1 to the n plus 1 over n. And then you'd see that this diverges, because it'll be -1 over n. It's not alternating, it's just a harmonic series with a negative in front. This one would be conditionally convergent though, because it would be the alternating harmonic series. Okay, so, does that make sense? Yeah, so that's exactly what will come out on this one. I don't want to get rid of this until you take your picture, Jack, or whoever else wants it. So go ahead and try this. I mean, the endpoints, this is centered at 3. Notice on this one that we actually have a lot of work to do. I can tell you what the radius convergence is, but you might need to do that yourself. So guys, the reason the problems on the homework are the same is because you should do this with your other homework by your side, right? You know what I mean? You have the radius of convergence already. So you can just, does that make sense? The only instructions difference here is that you're finding
We're going to discuss the main office. Schubert, Andy Lee,
think about
Green Shift, Valerie,
more endpoint stuff tomorrow. Don't worry.
Actually, I think I already
Wait. And I might give this out. It's more ridiculous. I don't know. You have no idea. I'm gonna give this out on Monday.
I really wish I read yesterday.